Okay, I want to do a quick example of a radiation heat transfer problem that involves only black bodies. And so at the end of last time, we said that when we have these kind of problems, we're going to rely on two sets of equations. The first is this top equation, which I can write for every surface, and it's basically just saying the rate of heat transfer from the surface by radiation is the sum of the rate of heat transfer from the surface to each of the other surfaces, and that's what's given by this summation here. So I can write this equation. This is one equation. I can write it n times. And then separately, I need a boundary condition for every equation, which says that I either know the heat transfer rate or the temperature or some relationship between them for every single surface. And if I can do that, then I have 2n equations and 2n unknowns, and it becomes an algebraic math problem that isn't very hard. The first step is actually getting all of the areas and all of the view factors, right? So I can only write these equations once I have those quantities determined. So here's the problem we're going to do. It's a radiation problem. It's a vacuum shield. So I have a tube running through the center of the shield here. It's got a diameter of 1.5 centimeters and a length of 10 centimeters, and its surface is at 77 Kelvin. So maybe we're running liquid nitrogen through this tube. In order to protect it from heat transfer, we are going to put it inside of another tube. So this outer tube is another tube, and evacuate the space between them, right? So it's just radiation that's going on inside of here, no convection. This outer tube has a diameter of 3 centimeters and a surface temperature of 300 Kelvin. And then we have these end caps that are necessary to pull a vacuum. So the left end cap is completely insulated, right? So there's it's not being heated or cooled. The right end cap is being held at 100 Kelvin, right? So these are our surfaces. There's 4 of them, which means that drawing a network would be confusing and difficult. There's surface 1, which is this inner tube. There's surface 2, which is this insulated end cap. Surface 3 is this other end cap. And then surface 4 is the inside surface of this outer cylinder, right? So let's do this problem in ease. The first thing I did here at ease is just put in the geometry of the problem. So these are my length, the outer diameter, and the inner diameter. The next thing I have to do is figure out all of my areas. So here you have to be very clear in your own head what surface is defined as what, right? So what is the area of the surface I'm talking about? So surface 1 is the outer surface of this inner tube. So that has area pi dl. Surface 2 and surface 3 are the inner surfaces of this end cap, right? So surface 2 is the right-hand surface of this plate. Surface 3 is the left-hand surface of this plate. So here's the area of those. And then surface 4 is the inner surface of this outer cylinder. So that's this area here. So I can go here and calculate them and make sure at the end of this that I have my area vector completely filled in. And the next thing I got to do then is figure out my view factor matrix, right? So I have 4 surfaces. Each surface has a view factor to each of the other surfaces. So it's going to be a 4x4 matrix that needs to be filled in. So how you do this is a little bit fun and kind of like a logic puzzle sometimes, but you got to start at some surface and just see kind of what you know and what you can get based on what you know. So I started here at surface 1, and it was pretty obvious to me that surface 1 can't see itself, so F11 is equal to 0. Surface 1 definitely sees surface 2 and surface 3. It sees surface 2 and 3 the same amount, so those two view factors should be equal. And then surface 1 also sees surface 4. So I kind of got stuck there, and I decided that I'm going to go see if there's anything I can get from the view factor library. So here's options, function information, heat transfer. Let's go down to the view factor library. This is a 3-dimensional situation, and if I scroll through here, this one here is probably useful to me, right? This is a cylinder to one of those end caps. So this is F1 to 2 or F1 to 3, right? And then you have to make sure you're calling it correctly. You know, you give it the radii and the length, and that's what I did here. You just uncomment that. So I'm using F3D6 to get F12. F13 is F12. So now I have F11, F12, F13. The only thing I'm missing is F1 to 4, and I can get that from the enclosure rule, right? The enclosure rule says that F1 to 4 has to be 1 minus whatever fraction hits itself, hits surface 2, and hits surface 3. So at this point, if I hit solve, I should see that the first row in my view factor matrix is filled in, right? And I can actually look at this and make sense, see if it makes sense. So this says that 2.7% of the radiation emitted by that inner tube hits one end cap, 2.7% hits the other end cap, but actually 95% of it hits the outer tube. And given that this is kind of a long, skinny system, that makes pretty good sense to me. All right, so I'm all done with surface 1. Now I'm going to move on to surface 4. So I already have F14, which means that F41 I get kind of for free. I can use reciprocity, right? So that's what this is. F4 to 1 is A1 F, that should be F14. A1 F14 divided by A4. So I still got to get F4 to 2 and F4 to 3. Those two have to be equal, right? So this to here and this to here. And then actually I got to get F4 to 4 because that's not 0, right? Surface 4 can see itself. And so, you know, again, I'm going to go see if anything in here is going to help me. And I think this is the one that helps me. This is from the surface to itself. Right? This is kind of a weird one. This is F22. So I call that right here. And this is this guy right here. Once I have, in this case, it would be F44. Then I know that, let's see, F44 is how much of this surface hits itself. I have how much of this surface hits surface 1. So now whatever's left over is how much hits the two end caps, right? And so if I want just how much hits one of those two end caps, I would take 1 minus F41 minus F44 divided by 2, right? So this is how much hits this surface, and then the other half of this stuff hits that surface. Right? So that's what I did here. And if I solve, I should see now that the fourth row is filled in, right? So apparently 47% of what's emitted by that outer shield hits the inner tube, 44% hits itself, and then only 4% goes off and hits the end caps. And that kind of makes sense, again, given what the system looks like. So now I got these two end caps. So I know right away that since I've already done surface 1 and surface 2, I can get F21 and F24 for free. You know, and again, you're using reciprocity to get that. This is a flat surface, so it doesn't see itself, so F22 is equal to 0. So F23 then is just obtained from the enclosure rule. So I do that right here. And I should see now that row 2 is all filled in, right? And again, should make some kind of sense. Surface 2, that end cap sees the tube pretty well, right? 24% of it. It sees that outer shield real well. It sees that other end cap way across the way pretty badly, right? This is less than 1% of the radiation is going to hit that other end cap. And the last end cap is really easy because the last end cap is the same as this end cap if you just flip this thing around. So, you know, here we've got whatever F2 to 1 is, that's what F3 to 1 is. Whatever F2 to 4 was, that's what F3 to 4 was, and so on and so forth. So at this point then, if I go back here and uncomment, this guy right here, I should see that my view factor matrix is completely filled in, right? And you know, again, just like everything, I guess, as an engineer, it's kind of important to look at these different numbers and make sure they make some kind of sense, right? So that's sort of the upfront work. Actually, in most cases, this is the harder part of the problem, is making sure you have good view factors. Once you have that, then the next thing to do is implement these equations, right? So, whichever form of these you want to work in, I'm going to, I think, do this one right here. And you want to do this for every single surface. So you'll do this in a duplicate loop. So that's what this is right here. This is Q dot I is AI times sigma times the sum of Fij Ti to the fourth minus Tj to the fourth, and I'm writing that from j equals 1 to 4, right? And if I solve now, you're going to find that you don't have enough unknowns, right? This is 4 equations, but there's 8 unknowns. The 8 unknowns being the heat transfer for every surface and the temperature for every surface. So I should be 27 minus, so 31 minus 27 is 4. I'm 4 equations short, right? So what are those last 4 equations? Well, the last 4 equations are the boundary conditions. I have to know something about what's going on thermally at every one of these surfaces. So some of these are pretty easy. So T1 is given. That's a boundary condition. T3 and T4 were also given. Oh, I went too far. I'm sorry. T1 is given. T3 and T4 were also given 100 and 300. And then this last surface here, it's insulated. So what does that mean? That means that there is no net radiation coming off of this surface. I have radiation heat transfer between this surface and all the other surfaces, but if it's not being externally heated, the net radiation from the surface has to be 0, right? So if I go back here and implement those boundary conditions, which I did right here, now I should have enough equations and enough unknowns, and if I hit solve, I'll get a solution, right? And if I go look at it, you'll see that now every place that I set a temperature, my solution predicted a heat transfer rate. Every place that I set a heat transfer rate, my solution predicts a temperature. So, for example, that inner pipe that was 77 Kelvin, the net heat transfer from that inner pipe due to radiation is minus 2.1 watts. So what does that mean? That means that there's actually a net heat transfer rate by radiation of 2.1 watts into that cold surface, right? If you go out to the warm surface, 300 Kelvin, the net heat transfer rate by radiation from that surface is positive. It's 2.267 or 2.265 watts. That makes sense, right? That surface is radiating to the colder surfaces that are surrounding it. This left-hand shield over here, this insulated shield, this guy here, I didn't know what its temperature was, but I knew that it was insulated. This is telling me that 279.5 Kelvin is the temperature that it would need to come to in order to have no net radiation heat transfer, right? This is the temperature where this surface here, if you look at it, this surface here is going to radiate to this surface and to this surface, and it's going to receive radiation from this surface, and that's all going to balance out to make this thing adiabatic, right? I can change these boundary conditions down here, and I don't have to change anything else in this problem, right? So for example, if I wanted to make the other side adiabatic as well, so instead of setting the surface 3 temperature, I could set the surface 3 heat transfer rate, and that's what I did here. And it's going to now tell me that those 2 surfaces now have 0 heat transfer, and they come to this temperature here. They would come to the same temperature, and that makes sense. All right. One last thing, I'm going to put this back. Just to be clear, is I don't necessarily have to know the temperature of the heat transfer. I can know, and actually more often than not, I'll know not either of those 2 things, but a relationship between them, right? So here's a situation that's a little more realistic where I don't know what temperature surface 4 is at, and actually neither do I know what the heat transfer rate is. What I do know is that surface 4 is sitting in a room, and the heat transfer coefficient is 5 watts per meter squared Kelvin, and the room temperature, the air temperature, is 300 Kelvin. So what do I do with this information? Well, now I do an energy balance on surface 4, right? And the energy balance says there's a convection heat transfer rate to surface 4 that has to be balanced by the radiation from surface 4, right? So the convection heat transfer rate to surface 4 is h bar times A4 times T infinity minus T4. That's going into that outer surface. And then Q dot 4 is the radiation coming from that surface going to these other surfaces. So this right here is a perfectly legitimate boundary condition. It's not giving me T4 or Q4, it's giving me a relationship between them. And if I want to look at how that works, I just come down here and get rid of the boundary condition I had previously for surface 4 and instead implement this boundary condition here, right? I still have 4 boundary conditions. Here's 1, 2, 3, and now this is 4, right? If I solve this, it's going to tell me that surface 4 is going to go to 269 Kelvin, and the radiation heat transfer from surface 4 is going to be 1.46 watts, right? 1.46 watts is the radiation heat transfer going from surface 4 to these other colder surfaces. That's also the convection heat transfer from the surroundings to surface 4, right? And typically, like I said, you would have an energy balance like this on pretty much every one of your surfaces because they're all interacting with other modes of heat transfer typically. All right, so that's the basic idea behind blackbody transfer, blackbody radiation heat transfer. And what we have to do moving forward now is start talking about real surfaces that aren't black. And that does get a little bit more complicated, obviously, but they are all sort of analyzed by comparing them to a black surface. So we'll have quantities like emissivity, which is basically how much radiation does this surface emit as compared to a black surface, right? So that's a number that has to be between 0 and 1. So we'll sort of talk about that kind of stuff moving forward and how to analyze more realistic surfaces than these black surfaces.